8.7 is on indeterminate forms in L'Hopital's rule. And while most of us probably wish that limits were gone, that we didn't have to do limits anymore, 8.7 is another section on limits, but fortunately it makes a lot of the limits we've done in the past a little simpler. And the premise of L'Hopital's rule is that if we have a rational function, and when we substitute in or take the limit, we get something that's indeterminate, such as 0 over 0, or infinity over infinity, or something of that nature, then it turns out that this limit is equivalent to the limit of the derivative of the numerator divided by the derivative of the denominator. Now, before we go any further, let's be careful what we're not saying. We're not saying that if we have a rational function, that the derivative of that function is just the derivative of the numerator divided by the derivative of the denominator. We saw way back when that if we have a rational function, to take the derivative, we have to use the quotient rule. So we're not saying that the derivative is the derivative of the numerator divided by the derivative of the denominator. We're simply saying that the limit, the value that we approach, can be found by taking the derivative of the numerator and the derivative of the denominator. And there are also other variations that we can look at. But most of the ones that we deal with will be rational like this. Sometimes we have to also do logarithmic differentiation of our limits, but we'll save a few of those for homework. So let's do an example of something that is a pretty easy limit to do. Let's suppose we have x squared minus 4 over x minus 2, and we look at taking the limit as x approaches 2. Now notice if we substitute a 2 in, we get a 0 on top, a 0 on bottom, which is indeterminate. So in the past, we did algebra to simplify this to something that was not indeterminate. But something that we can do is we can apply L'Hopital's rule. We can take the derivative of the numerator over the derivative of the denominator. And if we take that limit as x approaches 2, notice we get 4. Which in the past, the way we would have done that is we would have factored. We would have reduced, and when we substituted a 2 in, we would have gotten 4, which is the same thing. So, I mean, this still works, but L'Hopital's rule will make some functions that are more complicated or some that we're not exactly sure how to algebraically simplify, or some that might not be able to be algebraically simplified, make it to where we can do those limits. Let's look at the limit as x goes to 0 of sine 3x over 5x. Now, if we substitute a 0 in, we get sine of 0 over 0, which sine of 0 is 0. So we get indeterminate. And you may recall back in chapter 1, we had some rule about sine x over x. But if we forgot what that rule is, what that limit gives us, we can apply L'Hopital's rule. If we take the derivative of the numerator, that's chain rule, derivative of sine times the derivative of 3x. We take the derivative of the denominator, that's just 5, and when we take that limit of this, cosine of 0, remember that's 1, so we have 3 times 1 over 5, which for the most part is much easier than what we did when we had to do a change of variable and we had to remember that formula, that sine of x over x is 1. If we know that this is indeterminate in its present form, just take the derivative of the numerator, take the derivative of the denominator, and get an answer. Now notice we said if it's indeterminate. If it's not indeterminate, then we can't really use this. What do you mean, wages? Let's suppose we have something that's excuse me. Just make up something. That limit, 2 plus 2 over 4 is 1. That's not indeterminate. We know that that limit is 1, but if we were to try to apply L'Hopital's rule, the derivative of the numerator is 1, the derivative of the denominator is 0, well, that's undefined. But we know that limit's not undefined, because if we take that limit before we do anything else, we found out that that limit is 1. So be careful that we only use L'Hopital's rule at the correct time, that we use it for indeterminate forms. All right, let's do another one. Let's do the limit as x goes to 0. Let's see, let's do natural log of x over, not that one. That's not what I was wanting. Let's do x plus 1 over x squared. Let's do this. Notice if we substitute a 0 in, on top we get natural log of 1, which is 0. On bottom we get 0. So that's indeterminate. So L'Hopital's rule does apply here. So if we take the limit of this, if we take the derivative of the top, to take the derivative of this, that's u prime over u. So u prime, the derivative of that is 1. When we do the derivative of the denominator, that derivative gives us 2x. So if we put that over 1, we get 1 over x plus 1 times 1 over 2x. If we substitute a 0 in here, we get 0 plus 1, 2 times 0. So it turns out that limit does not exist. Originally we were indeterminate. We weren't really sure about that, but it turns out that our limit does not exist. Let's look at this top. This one is a little bit different than the ones we've done so far, because in its present state, this is not rational, but yet this is indeterminate. If we substitute an infinity in, if we do these limits separately, the limit of x is infinity. Remember, 1 over x is x goes to infinity. If we let our denominator get really, really big, that goes to 0. So one thing we can do is we can rewrite this so that it is rational. Well, how do you do that? Let's do this. Let's do tangent of 1 over x, and instead of having this times x, let's divide by the reciprocal. Notice if we do something divided by 1 over x, dividing by a fraction is multiplying by the reciprocal. So dividing by 1 over x is the same thing as multiplying by x. So now we have a rational expression that we're taking the limit of. Let's make sure this is still indeterminate. If we let this go to 0, or infinity, that goes to 0. So we have tangent of 0 on top. That goes to 0. Tangent of 0, as I meant to say earlier but didn't, tangent of 0 is 0. That's indeterminate. Earlier we got infinity times 0, which was indeterminate. Now that we have 0 over 0, we can apply L'Hopital's rule. So if we want to take this limit, let's take the derivative of the numerator and the derivative of the denominator separately. Then take the limit. The derivative of tangent is secant squared. This is chain rule, so we also have to do times the derivative of the inside. 1 over x, that's x to the negative 1, which the derivative, that'd be negative 1 over x squared. When we take the derivative of the denominator, we're taking the derivative of 1 over x, which is also negative 1 over x squared. Well, notice we have a minus 1 over x squared factor on top, 1 on bottom. So our limit is equivalent to the limit as x goes to infinity of secant squared 1 over x. If we take that limit, that's equal to secant squared of 0. Remember, secant is the reciprocal of cosine. So secant is 1 over cosine, so that would be secant squared. Cosine of 0 is 1. 1 over 1 is 1. 1 squared. So as messy as that was, our limit comes out to be 1. Just remember, this function, the function itself, is not equivalent to our original function. So we're not saying that that and secant squared of 1 over x are equivalent, because they're not. But they do have the same limit. They do have the same limit. So the trick here was rewriting this as something that was rational. This is rational and indeterminate. So when we take the derivative of the top and the denominator, it turned out we got something that we could evaluate. Let's see. One thing I didn't mention earlier is if we apply L'Hopital's rule and we get something that is still indeterminate, we may have to repeat. I'm going to just do one real quickly. We take the limit as, let's see. Let's do, let's just do this one. I mean, technically, we could reduce this, but I just want to illustrate the point. We know that the limit here, hopefully we know, is 3/4. If we were to reduce that, we would get 3/4. It could be that we have something that's algebraic or trigonometric or something that is more complicated than this, that this same principle applies to. But notice if we just substitute in directly, we get 0 over 0, so we're indeterminate. So if we apply L'Hopital's rule, the derivative of the numerator, we get 6x. The derivative of the denominator, we get 8x. That limit is still indeterminate. So we can do this again. So this limit, which is equal to that limit, is also equivalent to the limit if we take the derivative of the numerator over the derivative of the denominator. The limit of a constant is itself, which reduces to 3/4. Of course, we wouldn't have done it that way on that particular one, but just to illustrate the principle, if once we apply L'Hopital's rule once, we still are indeterminate, then we continue until we get something that's not indeterminate. Let's look at one more to illustrate one other technique, L'Hopital's rule. Let's look at the limit as x goes to infinity of 1 plus x to the 1 over x. Notice if we directly substitute, this goes to infinity. The exponent, if we take the limit of the exponent, that goes to 0, which that's indeterminate. We've said in the past any to the thing to the 0 is 1, but, well, what about infinity? We're not really sure. It could be that it's 1, but it might not be. So let's see, well, how can we verify that that really is 1 or that it's not? So let's call this y. Now, a technique that we've used in the past to get a variable out of the exponent was to take natural log of both sides. So let's take the natural log of both sides. And it turns out various properties of limits that we could move this natural log to the inside, and it's equivalent to the limit of whatever we get when we take the natural log of our function. Since we have natural log of something to a power, we can bring the power down. So we have the limit as x goes to infinity of 1 over x natural log of 1 plus x, which in its current state, this is 0, this is infinity. If we let this go, x go to infinity, that goes to 0. If we let x go to infinity, well, natural log of infinity is infinity. So we're still not there yet. But notice another way of writing the right side. Let's just move the x to the denominator. Multiplying by 1 over x is the same as dividing by x. So here, natural log of infinity is infinity. We have infinity on bottom. That's indeterminate. Now we have a rational expression that's indeterminate. So now that it's rational, we can apply L'Hopital's rule. So that was the whole purpose of rewriting it this way versus this way, so that it would be rational. A function over a function that when we take the limit is indeterminate. So now apply L'Hopital's rule. Take the derivative of the numerator. The derivative of natural log is u prime over u. So u prime. That's the derivative of the numerator. Now the derivative of the denominator is 1. So the limit of 1 over 1 plus x, if we let x go to infinity, well, if we take that limit, 1 over infinity, that goes to 0. Now we have to be a little careful because that 0 is not the answer of our original limit. That 0 is what natural log of our original limit is. Remember, we called our original limit y. So we want to find out what y is, and y is going to be our actual limit. So natural log of our limit is 0. So to undo natural log, we do e to the natural log and e to the 0. So e to the natural log undoes itself, and we get 1. So y equals 1, which tells us that that limit is 1. It turns out, maybe everything to the 0 is 1. Well, at least infinity to the 0, yeah, that appears to be 1. At least in this case. So that's another technique of applying L'Hopital's rule. But the key is always going to be, if we have something indeterminate, can we write it as a rational expression that's indeterminate? And if so, differentiate the numerator, differentiate the denominator, and try to take the limit.